My name is Daniel Krzywicki. I'm a technical lead at Faber Novel Technologies, and today I would like to tell you how to make event sourcing composable using functional programming patterns. So I won't be boring you with the actual story behind it, but just know that many of the patterns you're about to see are actually used on major production systems in our company. At the end of the talk, I'll also give you a link to the repo where you can find the slides and all of the code in this talk and even more. So what's the plan for today? Yeah. So in the first part, we'll define basic building blocks for event sourcing, and we'll see that an imperative approach has severe limitations in terms of composability. And then in the second part, we'll explore how functional programming principles can help us overcome these composability problems. Okay? But first, let's start with a quick recap. So how many of you have ever done event sourcing? Okay, so that's cool. I think I can skip with introduction. Well, you all know that it's about storing changes to the state of the system instead of storing the current state itself. So I'll just skip those. So what this talk is not going to be about is any particular framework or architectural concerns. I won't be speaking also about error handling. Instead, I want to focus on the programming part, on composability, and I want to show you how to design a simple but powerful API for event sourcing from a developer's point of view. So we first need to define some basic building blocks. So first, as a domain model, we'll be using turtles, common in simulation toolkits. So a turtle has an identity, a position, and a direction. Okay, and there are three commands we have for operating on turtles. We have one command to create turtles, and we have one command to make it turn, to make an existing turtle turn, another command to make it walk in the direction it is facing. So let's look closer at the implementation of one of these commands. So for example, the creation command. So if you look, at the return type, you see that we have an either. That's because we want to do some very simple validation. For example, we don't want to create turtles too far away from the origin of the plane. Otherwise, we actually create the turtle. Okay, so here's a basic demo of what code with such a model could look like. So we define a helper command, a composite command actually, where we have a turtle walk right? So it walks first and then it turns right. And then we can actually have a for comprehension where we subsequently call different commands. And finally, we can have a very simple unit test for the final state. Okay, so there is a slight problem in this code. Well, the state is spaced from step to step, but we can just use flatmap to avoid this. That's why we carried the functions in the first place. Okay, you'll see that it will be convenient also in the later parts of the talk. So we have a model now. So how can we then source it? So the simplest way is just to define some events, one per command. So we'll have a created event, a turned event, and a walked event, which each correspond to commands we've defined before. Then we need an event handler. So basically, at its simplest form, an event handler is just the function you use to fold a sequence of events. So if we look closer at the signature, you'll see that in the input, you actually take an option of state. We do so in order to be able to handle creation events when we don't have state yet. However, in the output, we actually, for the sake of simplicity in this talk, I will abstract from error handling. Not being able to replay persistent event is usually a very serious problem. So in this talk, I just consider that in normal condition, there has to be an output to the handler. However, instead of just returning the state, we wrap it in a sum instead. So why do we do this? Well, it's simply so that we can actually chain multiple event handler applications, right? Because a sum is isomorphic with just a state, but it's also a subtype of option, so we will be, without much boilerplate, we'll be able to use it to fold events. And this is an example of the actual event handler implementation. So we have a case for the creation event where we just create the turtle. We have a case for an event, a turned event, where we copy the turtle by making it rotate. And then finally we have to somehow handle invalid transitions. So again, there are better ways of modeling this kind of failure, but I won't be covering them today for lack of time. So an example of using this model, well, we have the initial state, which is just empty. Then you have a sequence of events, a created event, a worked event, a turned event. Replaying those events is just as simple as following them with the event handler. And then we can make a unit test to check the final state. Just note that I'm using .value, not .get. It's .value on the sum type and not .get on the option type, which obviously you shouldn't be using. So that's safe. Okay, but still there is a bit of boilerplate in this event handler definition. We can make it better by using a factory which would take care of all of boilerplate for us. So for example, we can make a factory like this, which will handle the errors for us and also wrap all the cases we want to support in the sums. So that's much more readable. So now let's look at the commands. So at the top, you can see the command before introducing event sourcing, and at the bottom, you see that we are actually introducing some indirection, right? Instead of directly changing the state, we first create an event, and then we've moved the domain logic into the handler to modify the state based on this event. Okay, so let's make a quick recap. So far we've seen how to model the domain and how to define events and event handlers at the simplest. So what more could we want? Well, there is one thing we still lack in this approach, and it's composability. Okay. So what's the problem here? There are two units of composition we can consider when talking about event sourcing. We may want to compose event handlers, or we might want to compose commands. Composing event handlers is very simple because they're just functions. So composing functions is all programming functional programming is about. However, composing commands is less trivial. Let us see why. So you might ask, why bother composing commands? Well, remember the walk-right function we had before? It's actually a composite command. We basically compose two existing commands to create a new one. Okay? How do you even source it? How about these? Turn around, where you compose two turns, or make a U-turn. So there are two approaches. The first one is to create a new type of event for every new command. The problem is it's not extensible. Let us see why. Consider we might have also other event handlers in our system. For example, this one computes the total distance traveled by a turtle. Okay? So every time we would add an event which is related to distance, we'll need to update any handler in our system which is concerned with distance. So basically, overlapping event semantics can lead to a model which is really, really hard to reason about. We could try to pull out some weird event inheritance strategies, but it's much simpler to just use composition. So the alternative approach would be just to define a small set of atomic events and compose other operations out of these events. Right? So walking right is just walking then turning. Turning around is just turning twice. Basically, this is what we would do without event sourcing. So why should it be any different now? So let us see how we could emit multiple events at once. So let's go back to our walk right function. So we replace the previous code, so now it computes events instead of a state. So what are we missing? We need a state here. We need to pass a state, right, to be able to generate the new event. We can do it by simply using the handler to replay the previous event on the original state. Okay? It's important to note that this new state only exists in memory. It's never persisted anyway. It only exists so that we may be able to emit a new event. And then we'll need to return something for our composite command. We don't have much choice here. We need to somehow be able to return both events. And obviously, for this to work, we need to be able to persist eventually multiple events in an atomic way. So we'll need some kind of abstraction like this, which is able to do this. And if the idea of persisting multiple events at once surprises you, just know that we are not the only ones to do this. Greg Young's event store is also based on the concept of atomic commit, which contains multiple events. The akka persistence API also allow to persist multiple events at once. So we can compose commands now. Are we good? Well, not really, because there are some limits in the code we just saw. A part of error handling, which forces us to do this for comprehension, this code is pretty much imperative. The problem with this is that it doesn't scale. Right? So we need to manually replay the events at every step. We need to make sure we accumulate events in exactly the right order, which is very error prone. And we also need to make sure we propagate subsequent events and state correctly, which is also error prone. So let's see how we can improve it. And let's use a more functional approach for it. Okay, so we basically have three problems we are seeking to solve. The first is how to replay intermediate events. The second is how to accumulate new events. And the third is how to propagate state. So let's start by the first problem, replaying intermediate events. So this is the code we want to improve. Okay, so this is just the demo we had before without even sourcing, but with this verbose first implementation. So we can all agree that it's very error prone and not very friendly to read. So how could we automate it? The replaying part, the subsequent replaying part. How about extracting this common logic into a helper function? So basically we have two cases we need to handle: creation and modification. Okay, and so this is the most important part of the talk, because basically the idea is that after creating the event, we will automatically and immediately replay it through the handler, and we'll associate to the event the state resulting from that event. Okay, so basically if we look at the type signatures of these helpers, we're actually lifting events into tuples of event and state, and this state is the result of that event. It's not persisted yet, so it's just virtual, it's just in memory. However, it allows us to compose and chain subsequent operations. And we'll see that this is very powerful abstraction. So if you come back at our example, basically we can replace it with such a syntax. We just have to source the commands, and we get the event and the state. We didn't have to replay it automatically. Okay, so this is how our target code looks like now. At least the replay is being done for us. We still need to accumulate the events, and we still need to propagate the state. But the first problem is solved. So how about the second one? We still need to emit events in the right order at the end. So what if we could somehow accumulate them at each step of the for comprehension? And that brings us to the next part. Remember our helper? So we're lifting these events into tuples. So what if we lift them into a class instead, so that we might write a flat map method on that class? We'll actually be storing a sequence of events into this class, not a single one, because we'll be wanting to accumulate them. So this is what this case class may look like. So we add a helper method to be able to extract the events while dropping the state eventually. And we can also define the flat map method. And as you can see, we're just generalizing the pattern from above. So we are first extracting the current events and the current state represented by the instance of this class. Then we're feeding them into the continuation, which is just a function from state to another sourced instance. We are then extracting the events and the new state. And finally, we are wrapping it all into another sourced instance, which contains the concatenation of events and the new state. Okay, so I hope you can see that it's easy to write a pure function to make it hopefully a monad. Of course, a flat map and a pure function doesn't make a monad. They need to follow and respect the monad laws. However, instead of proving that this implementation does it, I just show you that, well, it's actually only just a special case of something called the writer monad, which many of you may know. Right? So if you use libraries like cat or Scalezi, you can just actually redefine the source monad as an alias to the writer monad along with some helpers. So the real novelty here are those helper functions where we will replay events into a monad just after their creation. So we can update the return type of our helpers and rewrite our example just like this. So we no longer see the events. We just see the state resulting from the command. And if we compare it to the code without even sourcing in the first place, and you can see that it's basically the same code. If we actually move this helper inside the definition of the command, this code becomes identical. So basically, even sourcing becomes an implementation detail of your code. Your domain logic can focus on what's important, but just like asynchronicity with features, like error handling with other types, even sourcing becomes transparent. Yeah. So we can still extract the events at the end, right? So we can still source a new turtle, then make it work right, and finally extract the events. And so that solves the second problem of accumulating new events. So let's look back at state propagation. Well, obviously, just like we did before, we can use a flat map. We can give up on the syntactic sugar of full comprehension, just use flat maps, and then we don't have to propagate the state manually. It's not okay. So it looks like we're finally there. We managed to automatically replay, accumulate, and propagate the state and the events in a top safe and transparent way. Unfortunately, I don't have really time for it today. There are even better ways to propagate state because that is not really safe, because you can actually make a map here, and you can make some modifications which stay in memory and are not represented by events. So there is another better approach. You can find it in the slides in the repo. However, let's see what are the benefits from this approach. For example, one thing is that this monadic approach allows us to actually compose commands of different instances. So for example, we can easily write a function like this, which applies any modification on two turtles at the same time. So basically, what we do is we update the first, and then we update the second. We return a tuple of updated turtles, but underneath, the events for the first and the second one are accumulated. So basically, we can save them atomically into an event store as a single transaction. So of course there is a trade-off between consistency and scalability here, because if you want to update multiple instances like this, you need to make sure that their events end up in the same units of distribution, right? So it needs to be used with care. But if you're more concerned about consistency than scalability, that could be an interesting thing. Another interesting implication concerns concurrency, because as we see, we can actually now write declarative programs, which can be run on an instance to produce reified side effects. Okay, all the modifications we wanted to do with a turtle, well, we just get an object out of it. So the implication is that it's very easy to introduce optimistic locking on top of it. We can easily hydrate an instance by replaying the events from the store, compute new events using this program, try to persist the events if nothing else has changed since, and if it fails, well, we can just retry until it works, or we give up. So it actually allows us to have something similar to a software transactional memory using this syntax. So let's sum up. We've seen today that with what can be the basic building blocks of an event sourcing API. I hope you've seen. I hope I managed to show you why composability is important, and we've seen that the functional approach can help us achieve such composability, and in such a way that event sourcing actually becomes an implementation detail of our code. So if you want to play with the code, you can find it in the following repo. There is even more than what I have covered today. It's not a library though, but feel free to pick the code and play with it. So thank you for listening. I hope you enjoyed it. And do you have any questions?
Thank you.
How would you handle side effects in such code? Yeah, basically, would you use some kind of free monad or tagless final? If yes, how does your approach compose with those? And if not, how else would you isolate those side effects?
Mm-hmm. Actually, you don't do side effects in such a code. You only emit events, right? These events already reify your side effects. So what if you're asking is, okay, how could I have some side effects apart from emitting the event, right? The way we usually solve it is that we first persist the events, which represent the side effects we want to have, and then we have a projection, which is code, which streams the events and applies the side effects while guaranteeing at least once semantics. So we usually do it outside of the part of the code which actually creates the events. Because that way the creation is actually side effect free, so you can have optimistic locking on top of it and so on.
Hi, thank you very much for the presentation. The question is following: in your monad decomposition, or rather flat maps, you accumulate a state that exists in memory to later save it somewhere. What happens if your runtime explodes at the middle of it?
Well, obviously it only exists in memory. That's the whole point of it. I mean,
did you think about usually when you do event sourcing, you really care about the events and not losing them at all?
Well, it depends on the semantics of what you want to achieve. My assumption is that when you do when you do atomic simple commands, you want them to be atomic. And my assumption is also that when you compose commands, you also want this composition to be atomic. So basically, we don't want intermediate events to be persistent if we fail halfway through. Thank you all.